This is part 4 of the series Logarithmic, Exponential, and Other Transcendental Functions. In the last part, we looked at taking the derivative of logarithmic functions and logarithmic differentiation in general. And in this part, we're going to start by looking at what happens when we encounter a derivative or a function involving absolute value. If we assume that u is a differentiable function of x and that u doesn't equal 0, then we have a very familiar looking derivative. The natural log of the absolute value of u is 1 over u du. And that's exactly the same as when we looked at derivatives of any natural log function. So the absolute value doesn't do anything to the overall function. Let's see why that is. Let's start by looking at the positive case. If u is greater than 0, then the absolute value of u is just u. And so we replace that in our original function, and the derivative of the natural log of u is simply 1 over u prime, or 1 over u du. And that gives us u prime over u. Now if we take a look at the negative case, where u is less than 0, then the derivative becomes the natural log of negative u. And let's ignore for the fact that natural log is only defined for positive values. Let's see what ends up happening before we actually take a natural log here. The derivative of this is 1 over negative u times negative u prime. And you can see that the negatives cancel out. Negative divided by a negative is positive. And so we're left with the same thing, u prime over u. Ultimately what this means is that we can differentiate a logarithmic function involving absolute value just as we would any other logarithmic expression without the absolute value. Nothing is changed. Let's go ahead and work just a couple more logarithmic differentiation problems just to make sure we've got a good handle on this before we move on to integration. In this case, we have a function involving an absolute value. So we differentiate it just as we would in any other case. So the derivative of the natural log of the absolute value of cosine x is equal to 1 over cos x, so 1 over u, du, the derivative of cos x, which is negative sine x. And negative sine x divided by cos x is negative tangent x. So a fairly straightforward derivative. Let's look at one more example. Here we want to find the relative extrema of this function. So we're first going to go ahead and take the derivative, and then we'll use the first derivative test to find out where our extrema are. So here we go. The derivative of the natural log of x squared plus 2x plus 3 is 1 over x squared plus 2x plus 3 times the derivative of this denominator, which is 2x plus 2. That combines to give us this function. Remember that the critical numbers occur where the first derivative is either 0 or undefined. And this function here is 0 at negative 1. And it is never undefined because this doesn't factor. There are no real solutions to this quadratic in the denominator. Then we go to our first derivative test number line with our critical number here, test value of negative 2 and 0. If we plug in negative 2 into the first derivative, we see that it is decreasing on that interval. And if we plug in a 0, it's increasing on that interval. That makes negative 1 a minimum. If we take that negative 1 critical number and plug it into our original function here, that comes out to the natural log of 2. So we have a minimum of this function at negative 1 ln of 2. Now we're going to go ahead and investigate the other half of logarithmic involvement, and that is logarithmic integration. So we've just covered logarithmic differentiation. Now we're going to do logarithmic integration. Let's start out by recalling that the derivative of the natural log is 1 over x, or when u is a differentiable function of x, the natural log of u is 1 over u du. That naturally leads to, because of the fundamental theorem, the integral of 1 over u is going to be ln of u plus c. And we looked at that when we did the derivation of the natural log function. To state this just a little more formally, if u is a differentiable function of x, then the integral of 1 over x dx is the natural log of the absolute value of x plus c, and this absolute value is required because natural log requires a positive function. It's only defined for positive values of x, and this can be anything over here, so we have to eliminate the negative piece. And the integral of 1 over u du, where u is differentiable, is equal to the natural log of u, absolute value of u, plus c. So far nothing bizarre and unusual. We've seen this a couple of times in the past. Let's go ahead and look at several examples to see if we can solidify these concepts. In this first example, we have a basic idea. Now that we have the idea of logarithmic differentiation and integration, we know how to take the integral of 1 over x. But we're going to do the exact same thing as we did before, look for a u substitution. We're doing pattern recognition. We just have now more tools to use. So the first thing I'm going to do, I'm going to let u equal x, and du, of course, then is dx. So we've matched the x, we've matched the dx, and now we have the integral of 2 over u du. So we go ahead and pull out the 2, and we have the integral of 1 over u du. This exactly matches our primary pattern here, which is simply the natural log of the absolute value of u plus c. And then we back substitute our u in, and we have 2 times the natural log of x plus c, the absolute value of x plus c. But now we're going to use the power rule of logarithmic functions and pull this 2 into the exponent of this object here, and that eliminates the need for the absolute value signs, because of course any value squared is a positive number, so we no longer need the absolute values. So the final result is natural log of x squared plus c. In our second example, we're going to solve a differential equation. So we're going to do some manipulation first. We're going to put this in differential form and then begin again. So this is the function rewritten in differential form. We've just pulled the dx up to the other side, and then we can put in our integral signs, because to solve this differential equation we need to take the antiderivative of both sides. So the antiderivative of dy equals the antiderivative of 1 over the natural log of x dx. Now this is critical. Your choice of your u substitution is very, very important. If you picked u as x ln of x, you're going to have a problem, because that derivative is going to be 1 plus the natural log of x, and that doesn't match anything that we have. But if we choose u is equal to the natural log of x, you can see that what this is actually doing, we have 1 over x times 1 over natural log of x. So by using this ln of x, we can recreate that 1 over x term, and that gives us a match. So we have 1 over x and dx matched, and this ln of x becomes our u. So we have this. The integral of dy equals the integral of 1 over u du. And so we just integrate that as normal. This matches our exact pattern over here. So the integral of dy is just y, because we're integrating with respect to y. And that equals the natural log of the absolute value of u plus c. And now here we have a strange result, because our u was natural log of x. So when we back substitute, we have y equals the natural log of the absolute value of the natural log of x plus c. So kind of a strange result, but hopefully it's not too shocking. So let's go ahead and look at another example. As usual with these examples, feel free to pause the video and give them a shot before I go over them. Alright, here we have the integral of 1 over 4x minus 1 dx. I think it's fairly clear what our u is going to be, so let's just go ahead with that process. I selected 4x minus 1 as my u. The du becomes 4 dx, and we're ended up with du over 4 equals dx. When I substitute in matching the pattern, we have the integral of 1 over u, because u is the 4x minus 1, du over 4, which replaces the dx. We pull out the 1/4, and that becomes 1/4 times the integral of 1 over u du. That matches our pattern, which is 1/4 ln of absolute value of u plus c. We back substitute our u back into the original expression, and we have the natural log of 4x minus 1 absolute value plus c divided by 4. Absolute value is necessary here because this x value could go negative, and we can't have that. So there's your final result. Let's move on to another example. In this example, we're looking for the area under this curve bounded by the x-axis and these vertical lines. So to start with, we're going to go ahead and set up our integral, and this is going to be a definite integral in this case, and see what we get. So the integral then is the area equals the integral from 0 to 3 of x over x squared plus 1 dx. My u is going to be x squared plus 1, and the derivative of that, du, is 2x dx. We pull under the 2, so d over 2 is x dx. We substitute back in, and this x dx takes care of the x here, or I should say the x here and the dx here, and we have 1 over u, so it's 1 over u du over 2. Now you'll notice that I had to change my limits of integration because we're no longer integrating with respect to x, we're integrating with respect to u. So that's going to be when x is 0, put that in here, and u is 1. When x is 3, 3 squared is 9 plus 1 is 10. So our upper limit is 10. So you have to remember to change your limits of integration. Pull out the 1/2. So we have the integral 1/2 times the integral of 1 to 10 of 1 over u du. And that's just 1/2 times the absolute value of the natural log of u evaluated from 1 to 10. And that gives us 1/2 times the natural log of 10 minus the natural log of 1. Natural log of 1 is 0, so this is just ln of 10 divided by 2. Obviously, absolute value is not needed here, simply because it's a positive number, and that approximates to 1.1513. Let's see if we can squeeze one more problem into this video. Here we have a fairly straightforward problem. You may be tempted to use the numerator as your u value, but you'll notice that the derivative of this function is in fact that function. And remember that the concept that we're dealing with here is natural log, and so we're looking for a 1 over u situation. Now ordinarily, if you were just encountering this at random, you might not think of that at first, and that's why sometimes there's a trial and error to find your u. So let's give it a go. I picked my u as x to the third plus x. The du is 3x squared plus 1 dx, and that's in fact what we have here, so that matches. And so our integral becomes the integral of 1 over u du, which is the natural log of the absolute value of u plus c, and then we back substitute. We have the natural log of the absolute value of x to the third plus x plus c. Absolute value is necessary because both of these terms can go negative, and so the absolute values have to be there. That was a fairly straightforward problem, even though it may have looked fairly complicated at first. Alright, I'm going to go ahead and end this video with this problem, and we'll pick up with some more examples in the next video. So I will talk to you in the next video.